Okay, so our next speaker is Professor Abhishek Dhar from ICTS, and he'll talk about entanglement dynamics during free expansion of a fermions.
Thanks. Okay, so first I'd like to thank the organizers for the invitation to give this talk. Okay, so I'll talk about page entanglement dynamics, and this is work done with my colleague Manas, who's one of the organizers, and one of our really fantastic postdocs, Madhumita Shah, who actually did some really painful calculations. Okay, so like the talk is about a very simple non-interacting system of fermionic gas freely expanding. And the motivation, at least one of the motivations, was to understand the page curve in black hole evaporation. So that was the motivation. I'll try to explain a bit. And we have some results from exact numerics and hydrodynamics. Okay, so okay, so let me start with very few slides on black holes. I know very little about black holes, but I'll just explain what I understand about the information loss paradox. Okay, so basically a black hole is formed when like there's a lot of dust which collapses because of gravitational attraction. And if the mass is like large enough, it forms a black hole. And classical a black hole is something from which nothing can escape. So this is some recent image of a black hole. Okay, but then if you look at quantum physics, what that tells us is that a black hole is actually a system which can be described by a wave function. So let's call it, and in principle, it's a pure state. Let's call it psi. And then one of the interesting developments was Hawking's calculation that a black hole can actually radiate. And unlike what we learned in classical physics, it can actually radiate, and eventually it keeps radiating and completely vanishes into a pure radiation. Okay, so now what's the paradox? So basically the idea is that initially it's a pure quantum state, and the wave function has a detailed information of what the star is made of and so on, like what the atoms are, where they're located and so on. While the final state is just radiation, it's a mixed state and which depends on a few parameters of the original black hole, like the charge and mass and so on. And so it looks like there's lots of information, right? I mean, all these microscopic details are completely gone. And in some sense, this is the paradox. One of the ways of framing the paradox is in terms of this entropy function. So what Hawking did in his 1975 calculation, it's a semi-classical calculation for understanding radiation from a black hole. And what he showed is that the entropy of the radiation keeps increasing all the time till the black hole is completely evaporates. Okay, so the entropy, if you just calculate what's coming out, that entropy keeps increasing forever. Okay, so now another very important result was due to Page, who did a sort of very simple calculation. He just took a collection of qubits, which is in a completely random state. And what he computed is the entanglement between like two halves of this system. And so it's a maximally entangled state. And what you can show is that if you look at the entanglement entropy of one subpart, then it keeps increasing till you reach about half the system, and then it has to go down. Okay, so I mean, Page's calculation was purely a static calculation. There was no dynamics and so on. But what it suggests is as the black hole evaporates, I mean, the black hole you think of as a collection of qubits, and the Hilbert space, as it evaporates, the Hilbert space dimension is decreasing. So at some point when half the black hole has evaporated, what Page argued is that the entropy has to go down. Right. Now the paradox in some sense is because this is very hard to demonstrate in a quantum gravity calculation. Recently there has been progress and it seems that people have actually shown that you can recover the Page curve from a purely quantum gravity calculation. So perhaps there's no more paradox, but there are still people who think that maybe there are still some issues. Okay, so now Okay, so this is something taken from this Quantum magazine, which kind of states what the paradox is. So here, what I plot is like the entanglement entropy as a function of time as a black hole evaporates, right? So initially, it's just a black hole and there's nothing outside. So there's no entanglement between what's inside the black hole and outside. So the entanglement entropy is 0. Then as it evaporates, then what Page said is that it should go up and at some point of time, it should start decreasing. While Hawking's calculation seems to suggest that it keeps increasing. Okay, so that's in some sense also a statement of the paradox. Okay, so now let me just make one other comment before I start describing our model. That it looks like, very similar to the problem of the arrow of time, where, one question is like, if I just let a gas expand, like free expansion of a gas from, let's say, this closed chamber to another, I just open this cap here and it escapes into this other here. So at long times, what I expect is that the gas should become homogeneous, right? And so even though the microscopic laws are completely reversible, one will never see things going the other way, right? So and one can actually compute an entropy, which in this case, Boltzmann's entropy, which tells us there's an increasing function of time, which takes us from here to here. And you can't have things going the other way. Okay, so here the irreversibility comes because there's a coarse graining and so on. What we observe is a coarse grain description. In contrast, the black hole, the one observes there is in some sense microscopic irreversibility, right? I mean, the von Neumann entropy, which is a microscopic object, it keeps increasing. Okay, so now let me talk about what we did. It's a very simple model which tries to reproduce the basic features of the Page curve. And it's a dynamical calculation, like we want to know how things evolve with time. Okay, so there's a lot of earlier work by first starting with Calabresi-Cardy and then a lot of these other papers. And the most directly related to our work are these two more recent papers, which have almost the same basic idea that I'll talk about soon. Okay, so what the main results that we have are results from exact microscopic numerical calculations, and then something, it's just some generalized hydrodynamic calculations. It's basically kind of kinetic theory. And one of the surprises is that these two calculations agree quite remarkably. Okay, so of course we have no gravity, no interaction, so in some sense it's a very trivial model, but I think the model still captures some important aspects, namely that semi-classical calculations are subtle, and one of the things we find is that while the radiation entropy could keep increasing, but that doesn't mean that the system entropy will also keep increasing. Okay, so systems entropy can still follow the Page curve, while the radiation entropy can keep increasing. Okay, so there's no contradiction with that. Okay, so a second motivation, like which was clear from the talks earlier by Yuval and Rajdeep, is that entanglement is one of the important measures of quantumness. And understanding it in many body system is an important problem. But even understanding it in very simple non-interacting problems is quite non-trivial, I think. Okay, so this is the model that we study. So it's just a 1D lattice of fermions, non-interacting fermions. And so there are n sites which I'll call the system, and then from 1 to on this side what I'll call the reservoir. Initially this side is completely full and this side is completely empty. Okay, and so the Hamiltonian is just this. It's a free just hopping between sites with this parameter g, both in the system and the reservoir. And then there's a sort of defect at this site, which is kind of important. I mean, if you didn't have defect, then things would be quite different. So this defect is important in actually generating entanglement. Okay, so then what we want to do is we prepare the system in this initial state, and then we connect it to this reservoir and then just let it evolve. And then we ask what is the entanglement between this half and the reservoir, right? So, I mean, it's some way of like thinking of this is like this is the black hole, and this is when it's radiating particles, and we want to capture the entanglement between what's going out and what's inside. Okay. Okay, so these are already things that I think Rajdeep mentioned, that we are looking at non-interacting lattice fermions prepared in initial Gaussian states. This makes a lot of calculations easy. Okay, so and this is sort of important that at this interface there's a defect, and the defect can be just the hopping can be different, or I can put some on-site potentials at site 0 and 1. Okay, so that's how we introduce the defect. Okay, so maybe I should just mention that, okay, but yeah, maybe I'll come to that later. Okay, so this is how, this is the black hole, and what's going out is the radiation. Yeah. Yeah, okay, so it turns out that in this model, if you don't have a defect, then if you look at the entanglement growth, it's actually logarithmic in time. Okay, with the defect, you get a linear growth. Okay, so somehow the defect is able to increase the rate at which things get entangled. You consider defect it's still a quadratic? It still keeps the system quadratic, right? Yeah, yeah. And yeah, without the defect, you have to go beyond semi-classical hydrodynamics to capture the entanglement and so on. Okay, so so this I already said that the initial condition is like all sites are empty. Equivalently, I can just think of all like states up to in the Fermi level are all are occupied, and okay, so this corresponds to 1 at 0 temperature and 0 thermodynamic entropy. Okay, so now for Gaussian states, the 2-point correlation function basically contains all information about the state. Its time evolution is just like a non-interacting single particle, and from the correlation function we can essentially compute everything, right? So, for example, some other interesting quantities are just the density profile, which is the diagonal elements of the correlation function. The other thing that we'll look at are like after some time, how many particles have escaped, and what is the number fluctuations in the number of the particles that have escaped, and so on. So all these things can be computed from this correlation function. And then, of course, even the entanglement entropy is contained in this correlation function. So basically, for I mean, given that the density matrix of the system is a Gaussian state, if we look at the correlation matrix in the subpart A, then just the entanglement entropy is just given in terms of the eigenvalues of this correlation matrix. Okay, so this is the formula that again Rajdeep already mentioned. Okay, so numerically it's very easy to find, like for our setup, how does the entanglement entropy change with time? We just compute the correlation function and then find its eigenvalues and compute this object. Okay, so now I'll talk about the hydrodynamic description of the system. So it's basically like it's a non-interacting gas, and the hydrodynamic description basically says that you have a phase space density, which tells us like how many particles are there at position x and in momentum k. Right? So this is some coarse-grained phase space density, okay, so the particles are moving with some velocity, which is the phase space velocity, and they do not interact. So therefore, one knows that the phase space density will just evolve according to some Liouville equation. And what we'll see is that this is in fact exactly a coarse-grained Wigner function. Okay, so then we basically have to solve this equation with our initial conditions, and the initial conditions that we have are in this phase space. We have a fully filled Fermi C on the on this system part, which goes from -n to 0, and then this is the reservoir, right? So we start from some initial phase space density like this, and then we evolve this phase space density with these equations. And here what we need are, so what do we need to solve these equations? So the particles that are there, I mean, there's a defect here. So there's some transmission and reflection of these particles. So we have to take into account that into account. And we also have to take into account that it's a finite box, okay? So basically we have to solve this equation with these boundary conditions, that there's scattering of particles at this defect and that there's a finite box. Okay, so now once we know this phase space density, then how do you compute the entanglement entropy? So before going to that, I'll just talk about how one can obtain this equation from a more microscopic picture. So basically, given the many-body state psi, I can construct a single particle density matrix. And from this, one can compute a Wigner function, again, a single particle Wigner function. This is completely microscopic. This contains all complete information about the system. But if we coarse-grained a bit this in space and over cells of size h bar, then you would basically get this function, the phase space, sort of semi-classical phase space density, which is the hydrodynamic field. And this one can show satisfies exactly this equation up to corrections of h bar. Okay, so this is not an exact equation. It's correct up to correction factors of h bar. Okay, yeah. Yeah. Right, yeah, but this one won't show negativity, yeah. It's right, yeah. Okay, so now how do you compute entanglement entropy from this phase space density? So okay, so here we discuss this. So like the density profile, if you just integrate over all momenta, that gives the local density. And the hydrodynamic density, okay, so the idea is that you just assume kind of some local equilibrium, and at some point x, at some time t, if you take a small cell, then the entropy, you can compute an entropy which is just the usual fermionic thermodynamic entropy. Okay, so this is the usual thermodynamic entropy of a gas with some Fermi distribution. And so this was actually defined by Yang. It's called also Yang-Yang entropy. And it's basically a Boltzmann entropy. Okay, so now this has been used, it was proposed in various papers that this actually sort of captures the entanglement entropy. There are some arguments why it's so. So basically this is the local entropy, but if you integrate it over some volume, that gives the entropy in that, it gives the entanglement entropy of that volume. Okay. So you can calculate it either for the system or for the reservoir by just integrating the local entropy over whatever volume. Okay, so from our microscopic solution of the phase space density, we are able to compute the entanglement entropy of this part and this part separately. I mean, in principle, we know that SA is supposed to be equal to SB, but so this, here we have done some approximations and we don't know if this is going to be true. So let's see what this gives us. Okay, so we'll be interested in using hydrodynamics to look at how the density evolves. We started from a domain wall initial condition, right? All particles here and nothing here. So how does this evolve? And then how does the entanglement between what's in the box and the environment, how does that evolve? Okay, so we know two ways to calculate this, either from microscopics or from hydrodynamics, and now we'll sort of compare these two approaches. Okay, so yeah, so I already discussed this, but let me say again how we solve this equation. So we have this equation, and so if there were no defects, then and no walls or anything, then the solution of this equation is trivial. You just ballistically evolve this equation. And so once you have a defect, there's a lot of reflections, and because there's a wall, there are multiple reflections. So you have to basically solve this, you have to take into account, you have to modify this equation to just account for multiple reflections, okay? So you have an infinite, in principle, infinite number of reflections and transmissions, and that leads to this formula for the phase space density on the right half. Okay, when did I start? Sorry.
There's still time.
Okay, yeah, there's a lot of time, too much time. Okay, so yeah, so basically this is the solution. And now let me show the numerical results. So this is for the density profile. So initially it's all 1 on in the system, and it's 0 everywhere. So after some time it does something, and then okay, so for some time till it sees the wall, it evolves like an infinite system, and that's a simple solution. But then it sees the wall, and there's all sorts of things going on. Okay, so here I plot the points are from complete exact microscopic calculations for a system of like the system has maybe 100 sites, and the reservoir has maybe 1,000 sites. Okay, and the solid lines are from the hydrodynamic predictions. Okay, so you can see there's almost perfect agreement. There are some oscillations and so on in the exact calculations which do not show up in the hydrodynamics, but otherwise overall there's perfect agreement. And this is the current at the junction between the system and the reservoir. So I mean, till some time you see that the current is completely constant, because it doesn't, it's like you have an infinite system and their particles are just coming in and entering the reservoir. And then at some point it realizes that it's a finite system, and it starts decaying. Okay, and we studied 3 kinds of defects. There's something called a conformal defect, where the conformal defect is you put the on-site potential and the hopping in such a way that the transmission is independent of the wave vector. Okay, so that's a special kind of defect. And then there are 2 other kinds of defect. For all the defects, the initial part is the same. It's a constant. And then there's some power law decay of the current, which depends on what kind of defect you put. Okay, and this we can predict completely from the hydrodynamics, the different powers that we get. Okay, so so here you see a very good agreement between hydrodynamics and microscopics. And okay, so this time where the system starts seeing finite size effects is what I'll call the page time. And it has a very simple physical interpretation. It's just the time it takes for the fastest particle to go to the end of the wall and come back. So it's just twice length divided by the Fermi velocity. Okay, and then you see this power law decays, which are kind of non-universal. Okay, so now let's look at the entanglement entropy. Okay, and what I will call the hydrodynamic entropy. So, okay, so there are, so first of all, we calculate from exact numerics the entanglement entropy between system and bath. So that is the circles. So it goes up and then goes down. Okay. So the fact that you have initially the system, I mean, obviously it's unentangled, there's nothing in the reservoir. And at long times, all the particles escape into the reservoir. So obviously it again becomes unentangled. So that's obvious that it has to go up and go down. Okay, so that's what the numerics reproduces. And here, okay, so these are results for the, I think, the conformal defect. And here, so initially it's a linear growth in time, and at long times it's a 1 by time decay. Yeah, so there's an inverse time decay at large times and linear growth at short times. Okay, then what I plot is the system hydrodynamic entropy. So this is calculated from hydrodynamics using the Yang-Yang formula. So this is the blue rhombuses. And that basically goes up and goes down. Okay, so it more or less almost exactly follows the microscopic calculation. And then we have the reservoir entropy also calculated from hydrodynamics, which at short times it agrees perfectly with the system entropy, but at long times it keeps increasing. Okay, so here you see something very different, that the reservoir entropy does not follow the entanglement entropy, but keeps increasing with time. Okay, and this crossover again happens at this time scale, which we will call the page time, because that's where the entropy changes the increase. And so we see this really remarkable agreement between the microscopic entanglement and the hydrodynamic system entropy at almost all times, right? And the hydrodynamic bath entropy, it keeps increasing, and the system entropy has this inverse time decay, which can be obtained exactly from hydrodynamics. Okay, so I just want to show some finite size effects here, I mean, which are kind of quite simple here. So if you scale time by n and entropy by n, then like if you have results from different system size, they all collapse. And this one can again understand completely from the hydrodynamic calculations. Okay, so also the good thing about the hydrodynamic calculation is that we can calculate all these sorts of asymptotics, like both small time and large time asymptotics. So for at short times, this series converges very fast, while at large times you can do a Poisson resummation of this series, and you can and then again just one term dominates, and you can find how it decays with time, and you get all these power laws. And so at short times, the entanglement entropy always grows linearly with time, while at large times we get this decay where the exponent depends on the kind of defect. Okay, so it's 1 for conformal defect and 1/3 for the other defects. Okay, there's some other nice thing that we observed is that, okay, so this is also something that you all briefly mentioned. So there's an exact relation between entanglement entropy and full counting statistics, which was derived in this very nice paper by Click and Levitov. So basically, you can write the entanglement entropy as just a sum over all cumulants of the particle number. But what is interesting is that quite often just the second cumulant is enough to capture the entanglement. Okay, so in our system, for example, we find that, okay, so here I plot the second cumulant versus time, and it has the same form as the page curve. And in fact, here we compare the entanglement, which is this curve, and the second cumulant, which is this curve, after putting in the factors from this series, right? And we see that they agree very well, except near the page time where there's some difference. Okay, so the second moment, in fact, captures the entanglement quite well, which is nice because I mean that's easier to measure in an experiment. Okay, so in fact there are a number of other papers which have also observed this, and there are some claims that in some situations the second cumulant is in the thermodynamic limit, it's exactly equal to the entanglement entropy. Okay, so I have a lot of time, but I'll take questions maybe. So basically, what we discussed is that there's a simple model which at least captures some basic features of the page curve. I mean, clearly it's not a model of black holes, and maybe it doesn't I mean, the physics is completely different, but at least one of the interesting observations is that if you do a semi-classical calculation and then the entropy of the radiation, which in this case of the reservoir, this entropy is an increasing function of time, just like the black hole entropy. I mean, the radiation keeps increasing, while the system's entropy actually follows exactly the page curve. Okay, and so I said that using this semi-classical hydrodynamics allows us quite a very analytic understanding of the page curve for this simple system. And okay, so this is kind of surprising. We don't understand exactly why this coarse-grained entropy captures the entanglement entropy so well. I mean, it's probably because the entanglement entropy is maybe just thermodynamic entropy, and partly it's quantum correlations. And what this is capturing is more the thermal entropy part. Okay, some interesting problems that we are currently looking at is, so here we focused on just the initial state is a 0 temperature state. But like looking at finite temperature states, we expect that things will be quite different. And so, and then what is the effect of interactions? And the other interesting problem is looking at bosons. With bosons, one difficulty is because to create this kind of Gaussian states is is slightly more challenging. Okay, so I'll stop with that. Thanks.
Yes, we have time for questions.
So about these open problems, I would think that if you took a generic interacting quantum system and you started in some initial state which was, like a finite temperature state, meaning that its average energy would correspond to some, temperature, but it was unentangled, and you let it evolve, then you would expect the state to thermalize, meaning that wouldn't you just expect the entanglement entropy to sort of flatten out over some time scale which doesn't scale with the system size, remain flat, and then go back again to zero over a time scale which is of the order of the Heisenberg time? I mean, wouldn't that be the generic behavior?
No, I mean, but of course, you're saying with interactions, right?
With interactions, yeah.
Yeah,
okay.
I mean,
so that's what I meant by generic quantum.
No, so if it was in a closed box, of course, it would saturate and go to the thermodynamic.
And then, of course, also over some Heisenberg time, it would have to, I guess.
No, I mean, if it's an open system, of course, it will like.
If it's an open system, yes.
Yeah, then of course it would, but I don't know why Heisenberg time. It should probably, it's not, why is it a Heisenberg time? It will be some other time scale, like it will be the time scale for roughly half the system to escape.
Right. So that's what you would generically expect.
Right. Yeah.
Okay.
Yeah, but like how it grows and like time scales might be very different, right? Like here instead of order n, it could be completely different.
Right. And presumably you wouldn't be able to do a hydrodynamic calculation for that system, even if it had some conserved quantities for which you could probably write down hydrodynamics. But here the thing is that you have an infinite number of conserved quantities. All your NKs are conserved densities, and in this.
Yeah, but even here it's surprising that it works.
Right.
So I don't know why it could like.
No, I'm just wondering, is the fact that it works in some sense a result of there being so many conserved quantities, the system being integrable? Like, is that something which is helping you, or is it sort of surprising that it works despite the fact that it's an integrable system with?
Yeah, see, part of the entanglement is probably just thermodynamic entropy, right?
Right.
So that should be captured by hydrodynamics even for a non-integral system. But I am not sure. This is just a guess.
Other questions?
Yeah. Again, I have some basic question. So let's say I have some d-dimensional classical system, and I have a d-dimensional quantum system. So d-dimensional classical system, let's say it is in some mixed state. So that mixedness we characterize by its Shannon entropy. So for a d-dimensional quantum states is von Neumann entropy, that is nothing but upper bounded by the Shannon entropy, no? Because your entanglement entropy is nothing but bipartite pure state. I take the reduced part, this mixed state, I find its von Neumann entropy.
Right, yeah.
So that is upper bounded by d-dimensional classical system, is Shannon entropy.
Yeah, I'm not sure. Maybe we can discuss.
No, I'm saying that that's d-dimensional classical system, it's von Neumann, Shannon entropy. Quantum system is von Neumann entropy as upper bounded by that. Shannon is the upper bound of this von Neumann entropy. That's what I'm trying to say.
Okay, I'm not sure. Maybe we can discuss it.
Yeah. So another question, you make that statement that this coarse graining things, generally a Wigner function can be negative, but after coarse graining it become positive.
Right,
so coarse graining means coarse graining in phase space something.
In phase space, yeah.
Phase space volume.
Right, yeah.
So can we put some limit that if the coarse graining is that much, this is the minimum amount of coarse graining I have to do so that negativity will vanish.
It has to be order h bar.
Will it be the order of h bar? That is my question.
Like what I've seen, like there are various ways of coarse graining, but typically if you do it over order h bar, it works.
It works.
And say there are some exact results also, but this, yeah.
I see. Yeah, because H bar is, this is the something quantum things, because if I can probe within that, then the negativity will come, something quantum
Right, yeah.
signature we can see. Beyond that is like classical behavior we are seeing.
Right, yeah.
So it is expected that H bar would be that amount of code signaling I have to do. If I could do, let's say mathematically, H bar by 10, then again some negativity should observe, something like that.
Yeah.
So I had one question about your hydrodynamics. I mean, so the equations is same for the reservoir as well as the system.
Right, yeah.
Boundary conditions, initial conditions are different, right?
Right, yeah.
So is it that for the system, when you are, for the reservoir, when you are seeing that it is going up because you have almost 10 times the size, that somehow there's a time scale later which will bring it down, or you think it will just keep going like that?
No, what will go? The entropy.
The entropy of the reservoir, if you went to even larger times for some.
Okay, no. So eventually it will it will very slowly saturate. Right. Yeah. Yeah.
Actually, Abhishek, I'm just trying to understand. So, suppose I take a generic integrable model like the Ising, which can be mapped into
Okay.
free fermions and stuff, right? So there, I think if I let the system evolve and call half the system as the
Yeah.
reservoir and half of it as a, so there it grows and then saturates. You know.
No, if
Here,
it's a
what
finite
gives you
system,
this downturn.
if it's a finite, but if it's an infinite, then it has to go down, right? It will saturate to a value which, let's say, is the thermodynamic value. But if it's an infinite, then it's basically because you started with a finite energy which you are distributing it over
Yeah.
an infinite.
And also the other thing is that in this situation, the reservoir entropy
Yeah.
plus the system entropy, doesn't it have to go to zero because the total system is a pure quantum system and it's evolving under, or probably not.
The full EA, of course, it's zero, right? Yeah.
So,
You're saying the full
so
one.
when you plot this, you're plotting something else probably.
This one I'm plotting the of A. This part A plus part B is the full system.
Yeah.
I'm plotting the entanglement entropy of part A.
Wasn't this yellow thing the reservoir thing, or I probably missed
Yeah,
it?
so either you can plot the yellow thing is the reservoir entropy,
That's part B.
part B,
And you have integrated out the system there, right?
integrated out the system, and but this is using hydrodynamics. Okay.
Yeah, that's what. So the fact that it's deviating from the part A,
Yeah.
that's what I'm. So
Yeah.
then
So
you
if it
cannot-
was the entanglement entropy, of course, we know SCS should be identically equal to SB, right?
Yeah, so that's,
But that's not captured by the hydrodynamic calculation, right? Yeah. It's because it's from hydrodynamics.
So in this work, you have considered a one-dimensional chain of non-interacting fermions. So what are the expectations if you go to higher dimensions like 2D or 3D?
Okay. Yeah, no, that's in Rajdeep's talk, I was exactly thinking of this question. I think, I mean, the hydrodynamic calculation is, okay, one can extend it to higher dimensions, and it will be interesting to see. But we haven't done it so far. But I think it will definitely be interesting to see, because there are, I mean, like, there are predictions in.
You'll have to put a line defect to get up.
Right, yeah. So it's more, but maybe, yeah, I think I have to put it. Right, yeah.
I have. So you said that the hydrodynamics is good for when H cross is small. Physically, what does it relative to what physical parameter regime does this hydrodynamics hold true?
No, okay. I didn't say hydrodynamics is good when H bar is small. I would say like it depends on what you are looking
Force
at.
graining scale, but physically, in what limit is this? Valid? Is it large n? I mean, that can't be.
Yeah, large n is of course important. I mean, that's why we can do hydrodynamics. So large n is definitely important. Other than that, for example, if we didn't have the defect, okay, then the entropy, for example, this linear dependence would change to logarithmic dependence in time, which is a much slower, and that in some slower growth, and in some sense that is more quantum. Okay, so in that case, actually the semi-classical description breaks down, and people have discussed that you need to do something called fluctuating quantum hydrodynamics to capture those features. So then the semi-classical theory doesn't work actually.
One comment maybe that when you are taking the one particle density matrix, in general, it would of course have some psi bar x, psi x prime. And then when you are going to the Wigner and writing some local equation, there's probably some scale which you are, that's the scale, the typical range over which the, let's say, C dagger x, C x prime falls is probably something that you are integrating over and asking it to be just a density field.
No, okay, you're saying what is the coarse graining that we are doing? Yeah, the coarse graining over, you can just think of like over many cells. Like, yeah, large number, I mean.
The model you showed, which was a chain which is the system, and multi-chain which was your empty space. Suppose I take in the system chain one particle. So after some time, I will find a system with a superposition of the particle in the right part and the particle in the left part.
Okay.
This is exactly the partitioning beam
Okay.
to the entanglement entropy that I mentioned in my talk. So your calculation of the entanglement entropy actually includes contributions from a superposition of a single particle on the right and on the left. So it's not purely entanglement. It includes contributions which I defined as our enemies.
As? Oh, enemies, right, okay, yeah. So you would say that it's more classical in some sense. The entanglement by this process is more classical. Yeah, I mean, you could be right. I think that makes sense. Non-interacting, yeah, and I think in principle only for Gaussian states, I guess. No, so it's related to current collisions, but it's just the number, like how many particles have gone, and yeah, but it's related to second.
So which is kind of like 4-point correlator,
right? Yeah. But yeah, it's Gaussian, right? Yeah, everything is 2-point, right? Yeah, yeah, yeah.
Thanks.
Does the fail in which case? No, no, because this is, I'm saying the state is Gaussian, but the current, of course, you will have all cumulants. So those are not zero. Right, yeah.
This is always the connection with the current that is going out from the system and the rate of entanglement entropy, right? I mean, the DSDT
right, yeah.
and the current. So in this case, I think that holds. But I was just wondering, like, how well established is that kind of a relation for interacting system? Like, is that well known?
No, but even that you are saying DSDT proportional to current.
Current, yeah.
But that is also not true at all. It's not generally true in our case.
Oh, here also
not at all times. I mean, at maybe till the page time, it's kind of true. But after that,
the decay part doesn't necessarily.
Decay part, I think no. It does it agree? I don't think it. But it's not,
But so-
okay,
so it's not
if you
superhuman.
plot like the second, I mean, the second, the second cumulant and, sorry, the cumulant and the entropy, if you do the same plot for current,
Yeah.
you would not get like this kind of agreement.
The exponents, for example.
Yeah, but the prefactors are completely off.
So this relation is probably some semi-classical.
Yeah, this actually, I'm not sure where it comes. It's some semi-classical idea, right? Yeah.
Yeah. So it's not generically for
No, I
quantum
don't
systems.
think it's
anymore.
any.
So I had a very quick question. So at the end, everything is in the reservoir, right? So how do I interpret that the reservoir entropy is saturating to some non-zero value when there is nothing outside the reservoir? So it's so
No, it's essentially the thermodynamic entropy of in the reservoir.
I see.
Because everything is in the reservoir now, so it will have some thermodynamic entropy, right?
So this young entropy that you had, if I integrate over all space, it is not necessarily zero.
It's not, no, right, yeah.
Okay.
Right, yeah.
Okay, so we can, we have questions. If you have more questions, you can ask Abhishek. So let's break for coffee. Let's thank Abhishek first.